In this project, we propose an AI code assistant for Objective-C enhanced GNUstep tools like GORM. It provides real-time code suggestions based on UI layout and developer input. We analyzed architectural changes, identified impacted files, and modeled two use cases. Using SAM, we compared two design alternatives and selected a modular approach for better maintainability. Finally, we created a full testing plan and evaluating potential risks to ensure reliability integration. Due to the time limit, we're not going to go through one by one about the introduction and overview. If you want, you could pause the video and take a look. It's clearly labeled in the chart below. Now we're going to talk about the high-level conceptual architecture of AI module. Our AI code assistant integrates with developer tools like GORM to provide real-time code suggestions based on UI layouts and project data. It interacts with different system layers, using base for file handling and concurrency, GUI classes to display suggestions, and core base for data processing and encryption. The assistant communicates with a local or external LLM, and the distribution ensures that all resources are properly packaged into the final application. This architecture enables seamless integration without disrupting the existing GNUstep workflow. The low-level architecture breaks the AI assistant into 5 key components: prompt manager, captures developer prompt and UI context, and sends them to AI code assistant, which manages logic queries the LLM engine and logs results through AI logger. Layout metadata parser, extract UI layout data from NSView, enabling context-aware suggestions. This design ensures modularity, clear responsibility, and minimal coupling with GNUstep's core GUI, making integration smooth and maintainable.
I'll go through the current state of GNUstep relative to the enhancement. Currently, the GNUstep development workflow is largely manual. Developers design interfaces in GORM by dragging UI elements and then manually write Objective-C code in Project Center. This workflow lacks any dynamic connection between UI design and code generation. Key limitations include the inability to extract UI metadata, a lack of support for natural language prompts, synchronous operations that can freeze the IDE, and no standardized data formats for the internal communication. These issues severely impact developer productivity and creativity. Manual workflows slow down prototyping and increasing coding errors. Without automatic code generation, experimenting with UI layouts or rapidly applying logic becomes tedious. Moreover, system responsiveness suffers, especially if AI-assisted features are introduced. The proposed enhancement envisions a modular, asynchronous architecture where components are decoupled and communicate through standardized protocols. This approach enables real-time metadata extraction, AI-driven code suggestions, and flexible integration of new tools. It also improves maintainability and scalability by isolating failures and simplifying updates. Ultimately, the enhanced system empowers developers with a more efficient, stable, and future-ready environment.
In this slide, we identify the key stakeholders involved in our architecture enhancement. GNUstep developers care about low integration overhead and system stability. End users who are app developers want fast and accurate AI suggestions that don't interpret their workflow. Project managers prioritize smooth delivery and low-risk integration. AI integrators need flexibility and easy upgrades. We then compare two architecture options: embedding the AI directly into GORM or building it as a modular subsystem. While embedding is easier to implement, it tightly couples the AI with GUI logic. The modular approach takes more effort at first, but offers much better long-term flexibility and reusability. Here, we use SAAM to compare how each approach performs across key non-functional requirements. The embedded approach suffers in maintainability, reusability, and stability due to its tight coupling. In contrast, the modular approach performs positively in almost every category, especially in maintainability, testability, and availability. Based on this analysis, we recommend the modular design. It ensures clear separation from the GUI, supports independent development and testing, and aligns better with all stakeholders' needs. It also sets a solid foundation for scaling the assistance to other tools in the future. In this slide, we're going to talk about impacted files for AI assistant integration. We updated key files in GORM, libsGUI, and Project Center to support the AI assistant. GORM handles user input and display suggestions, while NSView provides layout context. We also created new classes to send promotes and process responses. In Project Center, we added menu option and in-editor support. These changes connect the UI with the AI assistant in a clean and modular way. In this page, we will talk about the architecture analysis of AI code assistant. We considered two architectural styles for integrating the AI code assistant. The client-server mode runs the assistant as a separate service, allowing the GNUstep IDE to act as a lightweight client. This makes the backend easy to scale and update without touching the front end. In contrast, the layered model keeps everything within one application, with a clear separation between the UI, AI logic, and data. This makes the system easier to maintain locally. Both styles are viable, but the choice depends on whether we prioritize scalability or simplicity.
The sequence diagram of the first use case illustrates how the AI code assistant integrates with the GNUstep development environment to provide real-time coding support. The process begins when the developer opens a project in GORM IDE, which they initialize the AI assistant. The assistant queries project metadata from the developer tools API to gain contextual awareness of the current development environment. When the developer hovers over the UI element, the IDE triggers the assistant to generate a code suggestion. To do this, the assistant analyzes the UI element and fetches relevant source files using Foundation. After retrieving the necessary content, it generates an appropriate Objective-C snippet. This suggestion is rendered as a tooltip via the GUI layer, providing immediate visual feedback to the developer. Optionally, the back layer is used to highlight related code in the editor. Finally, the editor can either accept or ignore the suggestion. Completing the interaction, the diagram clearly shows the sequence of activations and the flow of control between components, reflecting a modular and responsive design architecture.
Now we're ready to talk about testing plans for AI assistant integration. To ensure the AI assistant works smoothly in GNUstep, we designed a multi-layered testing plan. First, we do unit tests on promote building and code parsing. Then integration test checks how GORM and Project Center interact with the assistant, including undo and redo. We also test user experience, measuring accuracy and response clarity, and run performance tests with large projects. Finally, we handle edge cases and ensure security and stability. So even if the assistant fails, the system stays safe and responsive. Now it's time to sum up what we learned. First, through enhancement design, we learned how to identify features that are missing from the current system and clearly justify their value. During architecture modification, we explored how to adapt both high-level and low-level architectures to support our proposed feature. We also performed a component impact analysis, which helped us understand how specific files, modules, and interfaces needed to change. In terms of risk evaluation, we assessed the potential impact on system maintainability, performance, and stability, which gave us a better sense of architectural trade-off. The SAAM analysis taught us how to evaluate different design alternatives based on stakeholders' needs and non-functional requirements. And finally, by writing a detailed testing plan, we realized the importance of validating enhancements from unit level to system level to ensure quality and usability. Overall, this project gave us a hands-on understanding of real-world software architectural work.